Squeeze it a little closer, Jack.
Sure. Oh, yeah.
Okay, you're going to be here.
Okay.
And I will pass this to you when it's time.
Okay.
I'm going to start with this, Jack.
You're going to start using
I'm going to start using this. And I'll pass it to the board. This is one. Let's just start this now. Yeah. You and Bob will be near the center because your laptop and Bob's laptop will switch in. Cal? Do you need AC? Jack, could you just... Here, Mikhail. You don't have a laptop. You'll just talk, right?
I do, but
Well, you'll tell me.
I have a picture of the mastering chain that maybe I could show, but
Do you love the idea?
I don't know what, I missed.
I don't know where it would fit.
So I don't know what he's
We're going to talk. I want to talk about MQA.
It's not my phone.
I think it might be mine.
Where did Richard go? Hey, Richard. Who's talking?
Hey everyone, so welcome to our year's first AES event. I'm one of the student co-chairs here at McGill, and thank you for coming. So we're really excited about our panelists here this evening, and we welcome you to stay after the presentation for refreshments. If you're interested and you're not already on the mailing list, we have a piece of paper outside just in the little hallway if you want to just leave your name and your email. And yeah, without further ado, I'll hand it over to George, and enjoy.
I have to do that. I could have done that.
Well, you know.
Right. Hi, my name is George Massenberg. I've often been described as the motorcycle gang of the AES. Welcome everybody to the Schulich School of Music in the Elizabeth Worth Music Building of McGill University. And we're really glad to see you. This is our first shot, going out live web stream. This never works right, and we hope everybody will be patient. One thing we won't be doing tonight is doing retakes. No retakes. Don't ask. Tonight's subject is pragmatic approaches to high-resolution audio. Questions abound, and solutions are on the horizon. To me, and to some of our panel, this wasn't my original comment, but up until now, digital is but an unnatural act in between a microphone and a speaker. And my comment on that is I woke up at 4 in the morning, bolt upright in the bed, realizing that yesterday afternoon I had seen something that I had been waiting for 20, if not 35 years, which was a solution to some of our issues with digital. And so this has really been an existence-defining moment for me. And I couldn't be more pleased to have this extraordinary group of friends and panelists. So tonight we're going to talk about high-resolution audio, and we're going to talk about MQA as an enabler. Let me introduce our panel first. From the left, my friend Michal Jurovich, I've been practicing, but founder of Mytek, an extraordinary engineer, a designer, a high-end manufacturer, and someone who's very sensitive to high-quality audio. Also my friend, Bob Ludwig, a mastering engineer and evangelist for good sound, and the first engineer to master a high-resolution recording. On his left, also my friend, Bob Stewart, the founder of MQA, engineer, psychoacoustician, neuroscientist, a seeker after the truth. We like that. Sean Murphy, also an old friend. It's just great, you know. We should play poker. Producer, engineer, for both recorded and live music, so very unusual and many, many lessons to teach and a lot to learn from him. I'd like to start by talking to and hearing from, if we could, from Bob Stewart, and tell us what these features of MQA are that we've been listening to that we think are so important.
Do you want the 5-hour version, or should we do a quick one?
Well, I want the 20-hour version because I want all the details.
Okay.
But let's do as many minutes as it takes to cover.
Let's do a quick one, and we'll come back. And so I'll skip over some things, and you can ask questions at the end.
Hands to see how many people have even heard of MQA.
Ah, good idea. Beautiful.
Okay.
Cool.
Yeah.
So the picture on the slide at the moment. It's just reminding us that high-resolution sound, in fact, all sound, happens, we hope, in real spaces. And sound is acoustic, it's analog, and even when we speak to you here, this is analog. So these are just real performances, original performances, and his job is to take you back to that performance. That's what we're trying to do. So MQA, very quickly, we talk about 3 pillars of this. One is convenience. Convenience is important because we can have the best recording in the world, but if we can't easily distribute it, it's less useful. One of the things about MQA is that it is a smaller file, much smaller than the high-resolution file. It's typically a bandwidth of a CD, and it enables streaming, and we'll talk about that some more. Central pillar is sound quality. The fact that we reduce the bandwidth is convenient, but principally the quality's there. And one of the things that we guarantee is the actual sound that was heard in the studio. It was previewed or was signed off. And compatibility. This is what I call the last mile of the technology. When the customer has got the file, they want to play it back in all sorts of different places, in the car, on the computer, on your mobile phone, in a hi-fi system. And compatibility is important because we can't have a different file for every listening situation. So compatibility is important. The background to the thinking behind this really comes from wanting to address the state of the music industry. Now, I want to say at the outset, that this graph is not mine. This came from a selection of music label heads about the music industry's view of what they did to the quality of sound over really 50 years. And of course there are some high spots. And the fact that we show download as low quality here is more a comment about iTunes than about what you can get from HD tracks. But the general trend is there, and the reason this happened was convenience. Whenever customers find a format more convenient, they tend to go for it. And the convenience in some cases is quite critical. CD, you don't have to rewind it at the end, it's got random access, things like that. But what we really want to do is to stop having sound quality go down just because of convenience. And that's what we've been trying to do. So that's, if we could have both. So moving on, the way we achieve this, I'll talk about it a little bit, is by tackling 2 fundamental things. One is the digital process itself, and the other is the way that it's transmitted. But the insights behind it actually come from neuroscience. In 2006, there were some very important papers published that moved away from the previous sort of psychoacoustic viewpoint. And one of the things we've come to understand is that we should be always thinking of sounds in a natural context. Human listener, our hearing system is incredibly exquisite. It's very exquisite. It's a sense of survival. When your eyes are closed, you still know what's going on around you. When a sound happens, you can turn and you can point to it. You know how far away it is. And this ability has been, evolved in us over a long period of time. And we share the planet with other animals. Birds have a different syntax for speaking. Other animals have different syntax. But one of the most important sounds of understanding how the human hearing works is, in fact, the sound of the planet itself, is the natural sound, crackling leaves, snapping twigs, running water, rain, wind. These sounds have a very particular kind of mathematics. And one of the ways that we diverge with MQA from classical sampling theory is understanding this statistics and also the importance of some elements to humans. I'll come back to this one later, George. But one of the things that happens when we listen to sound is that our ears are continuously adjusting, and that was not considered before. Sounds that are transient and short, our hearing moves into a into a region where time is much more important than frequency, actually 5 times more important for anybody and up to 50 times more important for conductors, and somewhere in between, skilled listeners, which I hope you'll become, and musicians in between. The traditional view in which we have designed an audio equipment since, well, certainly since I started, is based on Fourier concepts where frequency is equally important. However, this isn't the case. Humans are more sensitive to time than frequency, and that means we have to go back and rethink quite a lot of things. So, this picture, right? The simplest path of a recording is to listen to the microphone output. And as George says, the digital channel is an unnatural act in the middle of it. Everything we listen to is analog. The microphone picks up analog, the loudspeaker plays back analog, and you hear analog because that's what travels in the air. Analog simply means sound is an analogy of the source, right? Doesn't mean that it's linear as opposed to digital. It means something very specific. And the problem with digital has been not that we don't know how to do lossless compression to move the data from one place to another, but how to move analog into digital and digital into analog. Those two gateways are critical. I'll skip over this. Classical digital sampling, which is based on the Shannon reconstruction theorem fundamentally, which that previous slide was about, drove audio down a path that was quite narrow in thinking about this. We ended up with brick wall filters, we ended up with linear phase filters that have this sort of pre-ring, post-ring characteristic. We have problems of quantization. One of the things that's very interesting about the ringing is that it happens at Nyquist, and you may think, as often we did in the early days, you can't hear that ring because it's too high in frequency. But in fact, neuroscience has shown us that in the brainstem, we have neurons that respond only to the envelope of the sound. Doesn't matter what the frequency is. So we actually hear this. And so in a digital channel, which is conventionally made, and with current DAC chips, all the hundreds of millions out there, the sound starts coming out before it starts. And if you think back to the picture of the wood, that never happens in the real world. When a twig snaps, doesn't work very well in here. The sound starts and then it decays, right? And we're very used to that. So with digital audio, with conventional digital audio, one of the problems we've had is that we had a thing that went at 4416, and we find that by doubling the sample rate, doubling it again, every time we double it, the sound gets a little bit better. But here on this graph, you can see that although the sound gets better, it only gradually approaches perfection. This is because if you've got a problem, you can't continue to make the horse go at twice the speed. Think about it like this. What's happening in the digital channel is that the filters on the input and the output and the quantizations are producing errors. And the analogy I'd perhaps use here is, if we've got a glass of water and it's slightly polluted, one way to make it more palatable is to pour in lots and lots and lots of clean water. But the other approach is to remove the pollution. And that's basically the analogy of what we're doing. You can go faster and faster and faster and spread out the errors. But if we do it right and we go back and remove the timing errors, remove the quantization errors, we end up with this picture, which is that we can get the sound of the studio at a much lower data rate. And that's what MQA basically does. So we end up in this situation. We're not thinking about the central digital path, because that obviously is straightforward to make lossless from whatever he decides in the studio is delivered. The key challenge is to deal with the converters at both ends and go from analog to analog. And that's the fundamental concept. And I think I would stop there.
Great.
We'll come back later.
Thanks, Bob. I appreciate it. Very clear and concise. And there'll be questions later as they come to mind. We also invite questions from our Facebook audience, which Jack will keep track of and throw over to us. And at any point in the evening, if you have
If you want these.
questions or something is really unclear, just stand up and do one of these and let us know. But in the meantime, I think it would be interesting to move from egregiously flawed audio to Nirvana, to put it a certain way. And I invite Bob Ludwig to talk about egregiously bad audio.
Wow. I can't believe there aren't more questions about Bob's talk. You know, you're just stunned, or
I know.
I think they come later.
okay, all right, good.
I've got questions. Why did it go on so long?
So I've been involved with trying to get sound as high quality as possible for my whole career, and this is a slide that really doesn't show you much about high quality sound. This is the first CDR recorder in the Western Hemisphere. And when I was at Masterdisc, we had the first one of these that Gotham Audio sold. That's is your pointer available?
Yes, it is. You have to plug that into a second USB.
Oh my goodness, I don't have a. Yes, I do have it.
Point. You just want
Just want to point.
Okay, there you go. It's threatening the battery.
There you go. This is the CDR recorder. This is $35,000 US in 1990. So what is that in these dollars, right? So that's the familiar. What am I doing wrong? There you go.
Got it.
That's the familiar part where you put the CD in the tray. Anybody guess what that whole, what is it, 2 or 3U rack is there? That's just the 8 to 14 modulator that ended up being a VLSI in all the CDR chips. I mean, the CDR players, recorders. And then in order to play back the sound, you needed a Sony 1610 with a DMR 4000, the Sony 1610 converter. That's a U-matic tape that stored all the CD masters. Up until not that long ago, every CD master on the planet was made using one of those Sony U-matic tapes, 3/4-inch tapes. This is Russ Ham and Joe Lee Young from Gotham Audio. And this is Daniel Weiss and Ralph Kessler made the Penguin software for the making the PQ codes for the CD. So between these guys were really expensive, and $35,000 for that.
And not very good.
Mm-hmm.
Not very good.
Yeah, exactly. And the discs cost $80 a piece. And so if you blew a disc because one of that complicated pieces of software didn't go right,
As they did.
and which they often did, you'd have to redo the whole thing. And of course, it was only at 1x. That was obviously the fastest the video deck could go. That was 1990. I think it was till 1993 that Hewlett-Packard finally made a CDR recorder that only cost $1,000. So, the prices started going down pretty quickly, but I just thought you'd be curious to see that. This is a Billboard article that says that I was the project I did was the first thing that was ever done in high resolution. So I was really thrilled when I heard that. We were very early adapters. We had the very first converters that were ever made, and we owned a Nagra D digital machine that could store 96 kilohertz using a dual wire interface, so we could actually archive the thing. But there was a couple of times when we had a converter that there was nobody on the planet that could play it, that kind of thing. So it's progressed quite a bit. But this part of my talk here is about anti-high resolution. This is one of the things we're involved with in mastering is the loudness wars. You've heard of that, of course, right?
But we think that's over, right?
Well, we hope it's on its way to be coming over at some point. But I have to say, George, in the last couple of years, it's gotten worse, actually. I thought it was getting better, and then it got worse. And what made it worse was the recording engineers, the mix engineers themselves got so paranoid that nobody would hire them that they pre-mastered their stuff and smashed their own material. It's like this wild lemmings to the sea act of self-destruction that's going on. And it happens all the time. And the thing is that when you're a mastering engineer, one of the things that I do is to determine the sweet spot of how the music ought to sound. In other words, with pop music, compression is part of your bread and butter of what makes a great pop record. I mean, the pop genre is loud. You know how loud concerts are. They're louder than is good for your hearing health. And you're trying to play it back on earbuds or a boombox and trying to get some of that energy in there. And compression is an absolutely vital part to making pop records. You really can't do it without it. The question becomes, once you've gotten that great sound, and people in the 1960s and 70s and 80s all used analog compressors and did that exact same thing, once you've got that, then that's what your mix ought to be. And this whole thing of just simply making it louder because you can, and because someone isn't going to hit you because you've done it, it's really so counterproductive. And so just the thing to keep in your mind is, as high resolution becomes more and more part of the culture, keep in mind that things like the loudness wars are the antithesis of high resolution. It's like, what's the point of making something in high resolution if it just sounds ratty, you know? And so I just want to give you a couple of examples of that. The thing that turned the corner a little bit several years ago for the loudness wars was when Metallica put out Death Magnetic, the album that was mixed. It was not mastered by Ted Jensen very hot. The thing was mixed crazy hot by Andrew Sheps.
He claims he didn't.
Well,
We know different.
he doesn't say he didn't mix it.
No, he didn't. He didn't say that he crushed it. He claimed not to have crushed it. To this day.
Well, I'm about to show you a slide that will prove that otherwise.
Good.
But the thing is that this record was put out on Guitar Hero first. And in order to it takes, I think, a month and a half or 2 months to program and code each Guitar Hero title. So they had to get all the stems from Andrew in order to encode it and to make the Guitar Hero part of it. And so the fans who bought the Guitar Hero thing got to know the album without all this bus compression and other things that they put on it. And this is a particular spot on one of the songs on the album, and that's what the waveform of it looks like. And this is what the Guitar Hero sounded like. Is there a way to make it louder?
They do it.
Okay.
Can do this and
It's
do this.
There you go. Yeah.
But don't get too loud. Let's try this. Oh.
It's good.
There. Pay particular attention to the space around the kick drum, the sound of the guitars. There's a certain amount of space in it for a heavy metal record, you know. Okay, and that is the commercial CD, the waveforms of that same spot on the commercial CD. That is... If you're going to tell me that's not crushed, you're lying. And once you take that, if I were to play just the CD compared to the Guitar Hero thing, it would just blast us out of the room. So it's been lowered in level to match the level of the Guitar Hero. 0. The commercial CD. They call that wimpy loud sound. So it's important as producers, and maybe some of you will end up being record company executives, and as George was saying, that the loudness wars are starting to end. And the reason for that is that Spotify, most of the streaming services, and YouTube now, just recently YouTube, are loudness normalized, which means they're trying to play everything back at the same level. So the louder you make your mix, the more this algorithm is going to turn it down. And thus, if you make something like the Metallica that's just super smashed, when you turn it down to the level of the non-smashed record, it just doesn't sound big. It sounds very uncompetitive. And people will not buy it when they hear the one that's more dynamic.
We're hoping.
We're hoping, yeah. So hopefully that, and if you can simulate this, if you go into your iTunes preferences and go to playback, there's a thing called sound check. And if you click that on, it will try to make all the songs play back at the same level. And I've got great slides I can show you later on. Well, I'm not going to show it to you later on, but I've got good slides where I could compare a Schumann quiet piano thing with Metallica, and they can coexist. It's really quite remarkable. So as loudness normalization takes over, and it is the wave of the future, no question about it. We're not backing down from that. And it's a standard that only got codified only a few years ago. So it's new. It's something new on the horizon.
But it's being accepted.
Mm-hmm.
Yeah, it's being approved.
Yep. So if you're a mixer, you should be mixing with loudness meters and all that kind of stuff, and start getting a feel for what the peak to loudness ratio of all your mixes are, and start having one open all the time as you're mixing and starting to get a feel for this stuff.
And the other thing that we need to stress is you need to educate your artists that when they take their reference home and they feel it's not loud enough, that you give them a little bit of a background in what they will face competing in the marketplace. Not only Apple, not only iTunes.
Yeah, I mean, I usually have this fairly long email I send to clients and tell them to put it into iTunes and turn sound check on and compare it with other things with the sound check on, and where it's more democratic. And a lot of them just say, well, make it louder anyway, because that's not right now. Like if I put it in shuffle right now, I'll hear mine louder, that kind of thing. So it's an education, and it's a mentality thing that has to switch. Some other things that are out there is watermarking. I'm a huge fan of Charles Ives, and I have this CD of this sonata with Hilary Hahn playing violin, and it was recorded at the Clubhouse. Yeah. And this is what the CD sounds like. And put your good money down and go to pay for this. This is what you get. Ever heard?
Piano with vibrato.
What's that?
Piano with vibrato.
Yeah, exactly.
It's on vinyl.
So this is the CD. to me, that's not a good thing. Now, I've spoken with some people at Universal, and they're well aware that some people are not happy with this. And Universal's a big conglomerate that bought up EMI and other labels and different people from different factions. It's a great case of a lot of times the left hand doesn't even know what the right hand is doing within sometimes even the same company, and I'm sure that's true for some of the other larger labels. And I know they're trying to correct this. I know that some of the streaming people are re-importing versions without the watermarking, and I think the watermarking has served its purpose as far as the record company goes. But just be aware that that watermarking exists, and you should. I suggest previewing anything you go to buy and make sure you don't hear any flutter in it like that, and because it's not a great thing. So, having heard that, when last April, when I've been reading about MQA, and when Bob Stewart wanted to come and visit me at Gateway, he came and played me some MQA files that were just mind-blowing. How wonderful it is. Just to be clear, there's three big divides into the MQA. There's the thing that's in some ways very important is the what's it called?
Authentication.
The authentication. Thank you. So when I make a file and I've approved it and the artists have approved it, hopefully the artist will have approved it listening through an MQA DAC. That thing will get authenticated, and when you play it back through an MQA DAC, it's going to know the analog circuitry in that very DAC that you have, whether it's a Brooklyn DAC or a Manhattan DAC or a Ultra DAC from Meridian or the Explorer, the little Explorer guys that they make. What's the new one that you're making? The Clef?
It's called the Clef.
The Clef. All that, the analog circuitry for that particular DAC is accounted for in the smearing, de-blurring circuitry. So when that green light lights on, comes up, I can be assured that you're listening to the right file with the correct provenance, and that everything about it is good. And it's that green light only comes on if everything is bit for bit perfect. If you were to lower the file a tenth of a dB or put in a tenth of a dB of EQ, it would go away. You would know that something's not right in the circuit. So it's very important. Then to me, kind of the middle aspect is the origami folding, which takes the 384 and the 192 files and 176.4 files, 88.2, 96, and folds that information down into below the noise floor of the 44.1 or 48K 24-bit file. And the math is brilliant beyond belief. There's quite a few articles now that are published about it, and for sure at the end of this, or during it, you can ask Bob ad infinitum questions about it. But it's a true mind blower. We have a SpectraFu spectrum analyzer that's on all the time in my studio that is looking at the analog output of my metering chain. So it doesn't matter what sample frequency I switch from, it's always on, showing the full spectrum of what's going on in my monitoring system. And to load up, we did this Daft Punk example. I worked on the Daft Punk record, and that was at 88.2, and we had this 44.1 file, and I played it back, and you look at the spectrum analyzer, and it looked like an 88.2 file coming from a 44.1 file. It's very mind-blowing. It means that the Nyquist-Shannon theorems are re-looked at in a whole new way. You know, what used to be true for your whole life doesn't hold anymore. It's like this is like a little revolution in engineering that nothing really led up to it. It's just suddenly popped into the world. And then the third part of it is the de-blur software. Like I have friends that have played this. The thing that to explain the de-blur software is if, say, you did a 96K recording session, and then immediately you downsampled it to 48K or 44.1, and you lived with that for the rest of, for months or something like that. You got to just really know that file inside out, and I'm sure it was a good recording, and your friend said, oh, this sounds great, what could be better? And then one day, God, I did that at 96, and you go back and play the 96K file, and all of a sudden, the blur is less, it's more clear, you're hearing more detail, more reverb, all that. That's that same kind of quantum leap that exists for already existing masters. I'm doing this thing for Steve Reich and None Such right now, the music for 18 musicians. It's a reissue of a recording that was done to DAT, 16-bit DAT. And Bob did a MQA pass of it for me on the de-blur. And the xylophones and marimbas in this piece, you play it back through the de-blur circuitry on the MQA decoder, and it's tactile. You can just hear space around each one of the mallets as it's being hit. It's really, really great. So and the fact that this origami allows you, once you're left with a 44.1 or a 48K file, that's streamable with a decent internet connection. So that's great. That means like the highest resolution digital is being played back, and from 96K on down, it's absolutely lossless. And above that, there's no audible difference. We can get into the math of it and say, well, that little bit of noise that has no correlation with anything except that it was created along with this music, that can be lossily compressed and put into the noise floor. Anyway, it's so exciting to be able to just, you can go to Tidal now, and there's many MQA.
We're going to demonstrate this in a minute.
Mm-hmm.
Yeah.
You can go on and get a little Meridian Explorer DAC or the Clef. When is it coming out? Soon? Maybe? Someday? Summer.
Yeah.
And you can experience these high-resolution masters that have been in the record company archives. And our hope is, for me, as someone that's involved with good sound, I'm hoping that the average person will pay their $20 a month to Tidal and the other streaming services as they come online. They'll hear this music and they'll start being really attracted to it. They'll notice that they get more emotion from the music because more of the music is speaking to their body, And I think it'll kind of take the wax out of some of their ears, and then when they go back and listen to their MP3s, they're going to go like, wow, I really liked that at one point. I'm really amazed, and hopefully it'll be a culture shift and the whole landscape.
We've just gotten a question, and I'd like to ask you.
Yeah.
This is from Korea. I'm starting to see, we've got a lot of people in Korea. I'm starting to see master version albums on Tidal, MQA, and I have a suspicion that a lot of the modern albums that are up on Tidal were not actually recorded at 88.2 or 96, such as Coldplay or Florida. What am I actually getting through MQA versions of those modern albums? And I think this question would either be to Bob Ludwig or Bob Stewart.
Well, hopefully, one thing like some of the places like hdtracks.com, David Chesky and Norman Chesky are very concerned about the provenance of every record. And it's one thing, for instance, like Blue Coast Records out in California. They make a lot of DSD recordings, and they will, but also do 96K and things like that. They know that a lot of their customers have like Mytek converters, or they have Ed Meitner's converter for DSD. And those converters could be better than the DAC that they're, the PCM DAC that they're using. And so Blue Coast will take some PCM recordings and put them out as DSD. But they're so clear about it. They'll say, this is recorded 96K DSD. We think it sounds best that way. However, we make a DSD version for those of you whose DSD DAC is better than your PCM DAC. It's your choice. So as long as the consumer is completely aware of what the provenance of the files are, I think that's great. And so they care a lot about that. hope, you hope and pray that the record companies are taking care of the provenance of the records that they're putting out for sale. I mean,
Well, you hope, but they
yeah.
didn't in the
I mean,
past.
I would be surprised if there's not some upsampled example that somebody can find. But for all the high-resolution files that we send to record companies, I feel confident that the things we send to them that are on HD tracks are being streamed at that same high res.
I know
Can I
you
give
have some more things in your
Can I give a
presentation.
short answer to that?
Absolutely.
So, I mean, as far as MQA is concerned, the agreements we have with the labels is that we have access to the very original, which is usually the highest resolution. We want to go back. Provenance is more important to us than numbers. So we want to get right back to the original master, which not the upsampled master or the equalized master, but the original. And as far as we can tell, we're trying to get the very, very best. Now, I think what the questioner is asking is about how he's hearing it, and I think if we can postpone that until I talk about the origami or the last mile and what each different listener might experience on Tidal,
Great.
we could answer it more clearly.
But I want to go on to the next thing that we plan to talk about, which is what do we consider to be high resolution? And I think it's an appropriate question at this time. Sean, you've been doing high resolution since your film score that you were talking about in '95.
We did a 192 film score in 2003. Not obviously at the time the hardware wouldn't allow us unlimited tracks of 192, but we a hybrid workstation with one set of converters at 192, another set at 96. We were always, and I do a lot of film score recording, we were always looking for a way to retain, and I know we don't want to talk about analog versus digital, but we were holding up our analog recording as the model for our orchestra recording that we wanted to try to replicate in the digital world. And we tried bit splitting, we tried various 2FS and 4FS conversions. And because we are pretty much in a multi-track world, we had to get to a multi-track situation where we could run at these higher sample rates and actually observe better quality recordings. We were thrown into that world full time in 2005 when we couldn't get the analog tape anymore for the Star Wars 3 recording. We sent the order in to Abbey Road for 150 rolls of Ampex 456, and they came back with not going to happen. Not even half that many available. You can have 40 rolls of 456, and you can have 30 rolls of BASF, and we're not going to do that. We're not going to mix and match like that. So we, at that point, we were thrust into the high resolution world. And
So what's your minimum standard now, if I may interrupt?
for orchestral
What would
recording,
you call high resolution for your industry?
I would say for our industry, I think it would be generally acknowledged to be a 96K 24-bit world. For me, it is more of a 192 32-bit world because I've gotten used to it and I'm spoiled.
And there's more resources, more hardware resources.
And now there is, right, and now there's become that. But sometimes we still make 2FS recordings because that is the standard either at the studio or for the production company that we're working for, so we say 2FS. I don't believe that a 2FS recording accurately replicates what we left off with in 1980.
With analog.
Exactly. And certainly not in film world when we were often recording on mag film, a 35 millimeter mag film with great big wide tracks and oxide, that's as thick as your fingernail and where you had almost unlimited level capability. And that kind of analog sound, if you get used to it, it's hard to divorce yourself from the knowledge of what that used to be.
Looking at the other end of this, how the consumer market. Where's the bar in the consumer market?
Well, maybe I can comment on this high resolution
Absolutely.
a little bit. Just an interesting thought when you think of half-inch tape and its 60 dB dynamic range and how good it sounds. My job is basically try to figure out the nuts and bolts of digital audio conversion and kind of correlate the parameters and performance of each circuit with the actual perception. And this example of analog tape versus 96, 192, or what have you, shows you that numbers are not necessarily that important always, and that correlates a little bit with what Bob said about how our brain processes the sound and what is actually important for our brain. And that's kind of what I'm trying to do in our work with converters, is to not only look at the numbers, but also try to understand how these numbers actually translate to actual subjective sound quality. And with what is very interesting with digital is that the recent boxes that we make, including this DAC here on the table, called Brooklyn DAC, are actually 32-bit, and I always get asked, like, why do you need 32-bit? It's 192 dynamic range. Why do you need it? And can you hear it? And the answer is yes, we can. So the thing with the analog world and digital, the numbers are behaving a little differently because of the nature of the digital artifacts that our brain cannot really handle very well.
Okay, you touched on something. I don't want to get too far away from it. Is what we've been talking about with temporal response. But I have one more quick question.
May I respond to that?
Mm-hmm. And you have to. But
Okay.
one more thing, just for the moment. Question, title has an MQA section, but do I need a decoder to stream true MQA? And the answer is
No.
right.
No, you don't.
Okay.
And I'll cover that in the
We'll
last
come back
mile
to that.
section. Okay.
But this thing about that we were talking about that I really don't want to let go of is the idea of the importance of temporal cues.
Yeah. May I answer your question about high resolution?
I hope you would, yes.
Okay. So, to my way of thinking, we have to look at the root of the word. One of the biggest problems the audio industry has got is this word high resolution, because it's been so abused. If we look at what we're really talking about, resolution means resolve. And in the optical world, resolution means, can we separate two objects? Can we see two blades of grass that are not blurred into one? And in sound, the same thing applies. Can we separate two sounds? This is resolution. And in my perspective, resolution exists as an analog concept and not a digital concept. So what makes high resolution in the analog world is where we have to start. And then we can design a digital system that doesn't mess that up. And one of the goals for MQA, our target, Peter Craven and I have this target that we want a channel that will do no more harm than sound traveling through a meter of air. Because we all live on this planet. The air transmits the sound, the air changes the sound. The further away it is, the dimmer it gets, the more blurred it becomes. But that kind of change to the sound is something that we know, we understand intuitively. You know, if you stick your head under the lid of a piano and you move slowly back, the sound gets progressively less bright. This is at least partly to do with what air is doing. And we think that we have to design our systems like that. And if you take that perspective, resolution should be defined in the analog domain, and we think it should be defined in how far away are we. And time resolution is part of that. If you want to locate something, if you want to know how big the object is, then the system has to have very fine time resolution. And the human has time resolution down to 5 microseconds. And that doesn't mean
or less.
Or less. And that doesn't mean we can hear 200 kilohertz. It means we can separate microsounds in the mid-range, actually typically in the speech band. You know, somebody walks up to you and whispers in your ear. You hear a lot more detail. And whenever any sound happens, you think you hear that once, but you're in fact hearing it 100 times. It's reflected off the ceiling, off the walls. Our hearing is programmed to deal with that. But we have to be able to separate those sounds. And if those sounds get smeared together, which is what happens with low bandwidth systems or bad filters, or it's what happens with lossy codecs, right? Sounds are sort of spread out over a week or something. Perceptually, it doesn't sound natural. So resolution to me is about getting the time resolution right, making sure that the noise floor of the system is entirely stable, that there's no modulation going on. And Miha's right. The The numbers don't necessarily map, because a 32-bit system is good because it's got lots of little steps, not because it has a dynamic range. But if you're smart, you can make the steps not matter.
So, Sean, this idea of complexity in the acoustic space around an orchestra,
Right.
Yeah.
are we thinking that that's improved by this greater temporal resolution?
Well, I think so. I mean, I think, and I'm new to this technique. We listened this morning, and it was very revealing that we could actually play back what was originally a 192 or 384 recording, unprocessed, and then compared to a processed version of the same thing at 44.1, and resolve the fact that they sounded very similar, and maybe the processed one was a little better in some ways, and it certainly suffered no ill effects, and in many cases suffered a lot of positive acoustical elements. So, I think continuing with what I was saying about higher sample rates, I think it doesn't mean we wouldn't still record at higher sample rates. What I think it means is we have to pay attention to this other techniques that allow us to, one, create files that are smaller in size. And I'm not saying that in the film world we care one whit about that. We could care less about file size nowadays. I mean, number of tracks, file size. But the fact that we can offer this level of resolution in something that is presentable at a normal sample rate.
And a reasonable stream speed.
Right.
Where we can
Well,
get something
I look at
very
it
quickly.
as even something, God forbid, that would fall into the Dolby world, where you could actually,
God forbid.
Yeah, which would actually deliver better sound to the motion picture theaters, better resolution within the paradigm of our music, sound effects, dialogue world. I was thinking that this morning when we were listening, that this is something that here we are at the same sample rate and the same bit rate, but with much, much higher quality.
Exactly.
Yeah.
My, how time flies. And I want to cover a couple of things that we had discussed, Bob's, if it's okay.
Yep.
One thing is that I want to straighten out that MQA's claim, as far as I can see, of being lossless is true. And that's non-intuitive to most of you, but something that we've come to understand. And there's the description of the origami and the process, and it's technical. And if you're interested, we'll go into that. But I'd want to cover one other really important thing first, is how to listen to music in evaluating processes and technologies. The listening test, the AB, the ABX, the ABC hid reference, the ABC my dog reference. Just kidding. Actually, that's not a bad thing to cover, because my dog can hear better than I can above 20K. And goes and runs under the bed when I'm playing anything with a Harmon mute, and a jazz band with Harmon mute.
Or a harpsichord, possibly.
Don't start.
Okay.
I have this really annoying harpsichord recording that David and I did. But I want to go to the important thing, is why has it been so difficult in the past to demonstrate a reliable test for sensitivity to higher resolution audio? It's been tremendously difficult to make some science out of it. And our pal Josh Rice at Queen Mary University of London has come up with a meta-analysis of all of the Hi-Rez papers, and has come up with a cross-section of positive results versus negative, but a pretty convincing cross-section that shows some 60% or higher assertion that there's some reasonably reliable testing. So what is it that keeps us from hearing it? You go home and you want to do a test? Here's an idea. Listen for longer. Listen for a minute and a half. Listen for 2 minutes. Put your iPhone away. Sorry. Sorry. I'm really. Put your iPhone away and just listen. And relax. And get immersed in the music. Note your feelings. And then listening to something else. You were mentioning something, Bob, very interesting about Uhashi and how long it takes to establish alpha waves.
I actually got a slide about that somewhere. If you want to see that?
Can we look at it?
Yeah, we will. But what you're talking about is a very, very difficult thing to do. To put a human listener into a scientific test to judge the difference with music. Remember earlier I said that one of the great things about our hearing system is it's so sensitive, but the other thing about it is it's so robust. You all know you can go to the pub and it's going to be really loud and music's coming through the ceiling. It's probably MP3, it's almost certainly MP3, but it's loud and you can still talk to each other. And we can communicate with a very small amount of information. So, well,
Nice one. Nice one.
no, that was. He knows that was 384, wasn't it? Kilobits. Yeah. So it's a very, very difficult thing to set up a test like that. And we did an extended listening test on just can you hear introduction of a filter into a high resolution chain, and it took us months. And I have to say, at the end of it, most of our participants wanted to slit their wrists, because when you continue doing an A/B, and at the end they said, "Well, great, but can we change the tune?" And we can't, because a scientific test requires consistent material, specific statistics, and in fact, our study was quite successful, and it ended up in Josh's paper. But it is a difficult thing to do now. Uhashi, who's been working on this area for some time in Japan, took 3 different approaches, one of which was to apply ECG and scan people while they're listening to high resolution and the same music with the high frequencies removed. And they proved fairly conclusively that there was a wholly different brain excitation pattern that happened when the high frequencies are there.
A different part of the brain.
Exactly, and it is in fact in the brain stem where we see it light up, which is where all the incoming signals are from the body and the ears, and it's not even clear which part of us is picking some of this up.
But we're thinking it's the amygdala, which is your reptile brain. All of you have a reptile brain.
Exactly. Yeah.
Some more developed than others.
Well, obviously, when you're a student, it's bigger.
I was going there, yeah.
So, sorry. What they showed was this rather clear result, but what they also showed was, and this makes it very difficult for A/B testing, that for the effect to build up, once you turn on high resolution, takes 2 minutes. And for the effect to die away, takes 3 minutes. So the idea of an A/B test, which is not switch, I'm confused. It has to be play a bit, have a cup of tea, play another bit. And that's quite hard to set up. Very hard, very time-consuming, very expensive. And also, finally, the last thing about an A/B test is that it drives the listener into the wrong mode. People get stressed. It's very difficult to decouple these things. I'm not saying we shouldn't do it. It's very important to do it, and you get the results, but it's not easy, and that's why it's not often done.
So now, at your company, do other of your colleagues at your company, are they trained listeners as well? Have you trained them?
We've used a cross section. We brought some people in, so we have audio engineers who've worked all the time. We've got musicians. They're quite interesting. People who
are trained listeners.
Trained listeners, but violinists playing at high level, cellists who play at high level. And the engineers will say, when you do an A/B, they say, well, this one sounds a bit rolled off. But the cellist will say, with the filter in, the cellist is no longer leading the performance. So it's a musical response that they get from it. And so this is tricky.
So Mahal, what about...
I just wanted to maybe give my example. I was doing A/B testing for 25 years, and I'm better.
You must be bored.
We all were. Boy, did we waste a lot of time.
I'm better than I was, but I'm not God. I think it has to do a lot with training and awareness. You have to learn it. You have to learn to listen to and how to listen. And I think that goes for musicians as well. They listen differently than engineers, and probably differently than mastering.
That's been proven. Yeah. In terms of that's the fascinating thing. In terms of time, frequency, resolution, I was talking about earlier. The average population is 5 times more sensitive, and then musicians are more so. Experienced listeners are more so, because it's an acquired skill. And in fact, you go on learning how to listen all through your life. And even if you have some reduction in high-frequency hearing, you don't lose as much from that as you gain from the neurons up to a quite late point. This slide here is taken from Ohashi and shows the way the EEG was giving a much more positive response to full range sound than to baseline, which is with high frequency cuts. But from the point of view of A/B listening, this is the one we need to absorb, which is that the excitation of high resolution builds up over 100 seconds, say, but takes ages to go away. So, I had my numbers slightly wrong before.
Well, that's okay. We're inspired. Another question from Korea. Is MQA just untitled just as a high-resolution file? No converter ringing removal without the hardware decoder? I know the answer, but perhaps you should.
So,
in other words, if he puts... The way I understand this...
I'll answer it this way.
Is it just a high-resolution file?
No. The MQA process involves, at the ingestion side, there is de-blurring and de-ringing of the A to D converter, whatever's in the master. Then there's a transmission file. And then when it's played back, the playback system, which either plays it back at single or double or natural speed, applies de-blurring, de-ringing for the converter that it's playing into. And so what's untitled is the real thing. It's identical to the high-resolution file. It's the file he made, or that you've made, streamed directly. And then it's up to you how you play it back. If you've got, if you've got an MSP DAC, or if you've got Mytek DAC, or you've got an Explorer, you've got a renderer, and other products will be coming out. You get more, but you still get at least double speed out of the Tidal app itself.
I'm going to go back to this question. How is, at your company, listening as a group, if you have other people you listen with that you can compare perceptions with, is there a difference? I mean, I find that there's a difference listening in a group.
Yeah, absolutely. I mean, we do it all the time. When we design a new box, we generally get several competitors' boxes, and we just listen to them and try to understand what they did and how they sound and what we want to do. And I work with Chebon, who's an engineer, and he has ear for recording music. My ear is more analytical. I look for very small details, like the decay of the bell or how much ambience and this and that. We listen often for different things. So you're right, when you combine several people, you can tell each other, oh, did you hear that? Did you hear that? And he may not have heard, but then on the second pass you do hear it.
I mean, I've learned a lot listening with these guys over the past couple days.
It is like that. It's back and forth. What I find very useful is using the same piece of music over and over for different tests, because I know it so intimately that I see what's happening with this particular thing on this particular piece of equipment, rather than listening to some random things.
Well, there's some evidence that our brain sort of maps our listening experience.
So it's definitely you accumulate the experience,
especially
and then you can,
as a music mixer, where you listen to a tune hundreds of times.
Yeah.
And for me, I map out things that are important and only hear the problems. So, and that's my feeling. Sean, you were about to say something.
Well, we have this experience in Boston where I make recordings with the Boston Symphony, where musicians come and listen in our control room frequently, and several musicians come in and listen all the time, wind players especially, and they can tell minute differences in level and EQ to the point where they can tell if we have an equalizer plug-in inserted but not on.
What?
On the buzz. In other words,
bullshit.
They can tell. They can say you've got something different. They don't know what. And
I didn't mean to say bullshit.
Yeah, but it's unbelievable, isn't it? That you say that. So you take it out, you take the plug-in off, you get rid of it, and they go, okay, that's what I was getting used to hearing.
It often is like this. You say something changed, and then you try to investigate, and it takes you forever to find out what changed.
Yeah, I'm sorry, I said bullshit. I didn't mean that. That's what you would hear from.
But this is, I think, it points to the acuity. that people develop when they're a player. A lot of players develop this. A lot of engineers do too. Trained listeners, someone who really is focusing carefully and knows what things are supposed to sound like. And we experience that all the time.
So the reason for my outburst is my next question was that even given the test results that we offer, sometimes scientifically supported, sometimes these results as having been vetted as credible, why are these results disparaged by the larger listener base? When I come back from an AES show and go on Reddit, I come out with 100 arrows in the back. Seriously, people saying, you know, why you can't hear that, I can't hear that, you can't. And these are not trained listeners, and
Right.
I'm not sure that they are easily trainable at a distance.
Well, I think it speaks also to the topic of comparisons and what they're listening on and how they perceive.
All the above their source material,
All the
their
above,
expectations.
right. If they were even involved in a test, was the test valid
So, Bob,
in any way?
Yeah.
given that you have this new source, do you expect this to change?
I hope so. But one of the things you have to understand is that if you go right back to thinking about temporal resolution, if we want to do a scientific study, which is different to just sitting back and enjoying the music, we have to first build a system which is better than our perception. And so part of what our journey is anyway on A/B listening tests is you have to keep making the system better and better, because in audio, and it's sad, all the research money that's available in universities, at least in the UK we've seen, has gone into two things. One is how to make the codec make it sound as low quality as possible for the phone. What's the worst we can get away with that makes you stop breaking the phone because it sounds so bad, right? And that's one thing. And the other is in hearing aid research, which is of course very noble, and cochlear implants, but there's no serious work done at the real end of the scale, which is where we want to operate, which is what actually can we hear, and you know, when do you get that limit, and what steps you back from it? And because of course we're working that limit, it is tiring if you listen in that way.
Nothing's harder.
Yeah, and so a better source obviously helps. We find, fortunately, you put a good master out, and people will listen to it. They'll listen to it on their phone, and they'll say, "My earbuds never sounded so good." And to me, that's really important, because although we have a sort of, as a group, audio engineers, we have a sort of elitist view that want to hear really good things. What this is really about is getting better sounding music to millions of people, and that's the goal.
So there must be some questions here. How can we have more questions from Korea than from...
Would you tell Mr. Korea just to send me an email? And it's fine, and I'll give him the answer. It's not a problem.
You'll not want this guy to have your email address.
Well, send it to MQA info.
Please. Let's get a microphone over here.
Hello. First, I would like to say that I'm very super excited to have you here, Bob. All the Bobs and yes. So I'm doing mastering. I'm having a small business, and I'm trying to do as much as I can with the resources I got. And I think it's very nice to talk about how to deliver these super high resolution files, but also in the first place we have to make them. And I come to the conclusion that I always have to upsample like crazy to get, the 32-bit and then the 192. But the thing is, how can we use that technology? Can we use that technology and somehow be able to use it for processing as well, so we can get rid of oversampling and?
It may be time to play something, because we've been listening to some music sources that are pure and simple. Just great performances, very clean, and you hear the artist's intent, which is what we come back to, is artist intent.
Yeah.
Where would you like me to
music.
start?
So what should we hear? We've got a bunch of stuff that we could play.
Sorry, I'll get rid of that picture.
Is that what we're hearing? Sorry. Wisla, what should we play?
Do you want to play stream or file or Bob's?
I want to play your files first and then play title
Okay.
myself.
Okay.
And I think that the thing that Wisla had earlier, and I've forgotten what it was.
Is this
Too much vodka.
Is this like we take requests?
Well, we're taking requests from the
While Bob's
faculty
getting-
first.
While Bob's getting that up, just to address your question a little bit more, I typically master at the sample frequency that the files come in on. You would think for most projects that there would be somebody overseeing the entire project and that the entire project would be at one sample rate in particular. That's seldom the case. So very often it's a judgment like, 90% of them are at 44.1, but this one guy that somebody else mixes at 96. What do we do? So sometimes in order to equal things out, we'll upsample things, and other times not. The upsampling is tricky. Someone like Chris Lord-Alge, for instance, who, when you send something to Chris, he'll put it on his Sony Dash machine and then mix it through an analog console and then re-record it at 96K, even if the masters were at 48. So it is upsampling, but on the other hand, once it's gone into the analog domain like that, all the harmonic distortion and other high-frequency things that the engineer thinks are good, quote-unquote, to the sound, because it creates the sound they want, the output of that console is more accurately captured at 96K than it is at 44.8 or 48 or 44.1. So it's, from an engineering point of view, it's totally legitimate. It's just that, as the guy from Korea was questioning, it's easy to not follow, just as people don't care about credits anymore, a lot of people don't care about the provenance, and it is important to care about it, and it's good to know that, this was mixed by Christopher Lord-Alge at 96K on an analog console, and it came from a 48K master. End of story. That's all the consumer needs to know, and it's completely legitimate. But that's how we work. Is
oh, come on! The first 70 years of the record business, there were no credits. Well, there was a producer and the artist, of course.
Mm-hmm. Okay.
But engineers, producers,
they are still on the tape boxes.
On the tape boxes, maybe, but not on allmusic.com.
But George, for the first 70 years, there was one product. Everyone put their energy into making the vinyl disc, and then you chose how to play it back. There weren't 56 different kinds. You didn't go to the store and say, I want the MP3 version of the vinyl disc.
Oh, no, there was a cylinder, and then there was that round thing, and then there was the little round thing.
Yeah, I wasn't going quite that far back. Before we play the music, can I just pick on two things? I think it'd be good if I showed one picture about de-blurring for people, because I think, and the other is, I want to address one of the comments you had in order that you don't get 1,000 comments on your Facebook feed.
We already do, huh?
You already do. Well, that's fine.
Go away.
Mm-hmm.
This just shows for 192 kilohertz sampling, the envelope, the energy of the impulse response because of the pre-ringing. And this is a typical chain. This is a 192 studio A to D and a studio DAC. And the degree of pre-ringing, which is definitely audible by the human, and the post-ringing is there. The original signal was an impulse, and what the MQA system does is gives us this very, very narrow impulse response. So when they talk about de-blurring, de-ringing, basically what we're talking about is removing that particular pollution as well as the quantization pollution. Now, your lossless question, when you do that, that is not lossless. We're taking poison out of the file. What is lossless is that when it's being prepared in the studio and Bob's listening with the plug-in and he's listening to exactly what will be delivered, that sound is delivered losslessly. And this is where one of the confusions come in. How can it be lossless if you're making a change and so on? So you hear
for the better.
And you also hear the result of the origami, and so whatever it does comes back. So you're actually approving the actual sound.
So Bob, if just to separate these two things, the blurring from origami, can you explain that a little? The processing itself happens at the high sampling rate, and the origami is the second step.
The de-blurring on the input side happens at the input. It's done at the encoder. It's the first step, and it depends on the sample rate then whether origami is used or how much of it is used. These are kind of two separate things, except that the de-blurring is inherent in the origami when the sampling rate is like 192 or 384 or 768 at the high rates. They're kind of coupled as effects. And we're not breaking Shannon. In an MQA file, we fold it so that each sample has got 3 bits of information in it. So when we open it, we've got 2 bits of information, open it again. And so Shannon wasn't wrong.
Well, the math is right.
The math's right. What's wrong is the insight, because one of the things that drove us to this is that in other areas of human endeavor, digital sampling has evolved much more quickly than in audio. Audio, when it went on a tram line, maybe because we had chips and we had no choice. But if you look at medical imaging, where I live in Cambridge, the researchers there are regularly getting to 3 times the Nyquist limit in terms of information that's extracted, because they know, as we do, we know the statistics of the music, and that helps a lot. Music is not rectangular, music is triangular, and if you reconstruct it in this way, it's you get a much more effective result. Another area is like in optical astronomy or in digital astronomy, you find that techniques allow us to get way beyond the Nyquist limit. You can't find a planet circling around a star unless you go beyond that limit. So it's just a question of opening up audio to this kind of technology. Have I lost the plot to this?
No, it's excellent points, and I'm really glad you brought them up. But can we hear some music?
Yes. So
Can we rock? No. We
yeah. Well, how about Eric Clapton, B.B. King?
Excellent.
That's what you wanted, wasn't it? Let's hope this works. No, don't tell me that. Let's do it again.
Okay.
So when it comes to provenance, that was an 88K recording, came out in 2000. As to upsampling or not, we always ask for the original asset. If you go and look at what 2L does, MQA always specifies recorded at original sample rate. So if something's recorded at 44, that's what you'll get. We're not trying to sell high resolution. We're trying to deliver the authentic sound. If it's 44, it's 48, or it's 88. If he took a thing in and decided he wanted to upsample it in order to do a certain kind of remastering, that's fine with us. The only thing we don't like is egregious upsampling, which is...
In this case, I did this recording, and that was at 88 too.
Yeah.
So, yeah.
Yeah. Good.
Yeah.
You did
Bob.
a great job.
Oh, thank you.
Bob, can we hear the Morton Lindbergh thing? With the,
Sure. You want to do it from file or from title?
Let's do one more from file.
So, which one had you in mind? Okay, I'll get it.
While you're looking for it, let me...
No, that's okay. I'll play the...
But we had a question from Ottawa. How does MQA handle DRM, embedded DRM? Now, you've answered that, so let's make that point again.
MQA has no DRM.
Right.
Zero DRM. Digital rights management means that you're prevented from doing something in the field unless you have a kind of key or permission. Right? There is no DRM. Everybody can hear the file. You can play it anywhere. You can put it in your phone. You're going to get better than CD quality if there's no decoder there. Everybody can hear it. What there is a secure signature. We use strong signature to protect the light. So when he says it's right, The light comes on at the other end. That isn't interfered with. And this is what sometimes gets people confused.
By the way, if nobody has noticed, Apple has dropped DRM now for a long time. And the reason they dropped it is it did not improve the business case.
No, it's hopeless.
In fact, it probably deteriorated in part because of DRM.
So you could have a piano, or you could have the Frank Bridge Romance.
Sure.
That one? Okay.
Is that the violin thing that starts with the violin, comes in with the chorus?
You want the violin concerto?
I think that's it.
The one that
If you,
Okay, well I'll play the piano first. So this is a jazz piano. This is everything that I play from Tidal is originally recorded at 352. Okay, so. So
any
that's.
questions? Any thoughts?
Let me play the Frank Bridge variation, and then you ready for the next one?
Mm-hmm. Being played back from a 44.1 file.
And it just is pleasant, so pleasing to listen to.
A couple things we've noted, and I think we should talk about that we tend to listen longer. I mean, most listening tests narrow down the length of time of your sample. Legitimate, qualified listening tests. But we don't think that's right. That you want to listen longer than that. And with MQA, it's kind of pleasant. I found, that's just a personal report, and I think my colleagues agree, is it's not as, you're not as anxiety prone. It's not very scientific, but that's
Well, that's the thing you have to try and measure in a listening test.
we need to measure it.
And in fact, I think we will get objective data, because on some of the streaming services already, we know that it's been seen that if you offer MP3 and you offer lossless, that people skip more often on the MP3 and go on to the next song than they do. And so maybe when we've had this out for 6 months, we'll see what happens on on masters, do they just listen to it all night? Or yeah, see, it'd be interesting to see.
Should we play title?
Sure, I will certainly attempt it.
Should work.
Yeah. So.
Hey Bob, is it possible to show this?
I'm sorry. Yes, I don't know why PowerPoint. Maybe I'll just shut PowerPoint down. And then we
okay.
Question from the audience: are there any limits as to what transport media can be used? And I think I'll answer for Bob. As long as it's as long as you have a 4824 stream.
It's, as long as you've got a bit accurate transport, it can be sent over Wi-Fi. It can be sent as a file. It can be put onto CD. It can be put onto DVD. It can be put onto Blu-ray disc. It's PCM. Everywhere PCM can go. I haven't explained the origami here, but the origami takes a PCM file and it folds it into a smaller PCM file, which you can play back without a decoder. And anyone who does that playback, you get slightly better than CD, or sometimes significantly better than CD quality. And this is one of the things that's unusual about it. It means that everybody can hear it without buying anything. And then, in some circumstances, you can have a great DAC in your living room and listen on your phone, and maybe there'll be a decoder in the phone and that sort of thing. Okay, we're going to play this.
One question from a technician. Are there any limits to what transport media can be used? Works on HDMI, works under DHCP, not DHCP.
Yes, works on all of
HDCP.
HDCP works on Chromecast, works on AirPlay, works on...
Great.
Anywhere PCM file can go. Because one of the things we did was to make sure it just looked like PCM so that it couldn't be stopped from going anywhere.
So we're listening. We've got... What you see is...
Yeah, go ahead.
Yeah, no,
Right.
you're the cat.
Well, I'm trying. So we're going to stream this from Tidal, and in this case, the data rate, the original is 352. In this case, this piece of music, the mean data rate is 1.3 megabits per second. We're going to stream it over Wi-Fi. See if it gets there.
There you are.
Good ending. Okay. Time for a fade. Not sure what happened. Oh, it's because I closed the other thing. I'll come back to it. Play some more in a second. Okay.
Any thoughts, questions, observations? Can you stand up, anybody? Can you stand up? Do you mind?
Hello. I'm sorry. All right. So I have another question. So here in this case, one of the problem arises first because we're using linear phase filters, which are basically doing the pre-ringing thing, then the impulse, and then it has the other ringing. Would it be possible to conceive another type of filter, which would be only the impulse? But I think a filter that is not linear has the impulse and then the ringing only afterwards. But it brings, of course, other phasing issues.
Well, everything in the natural world has a causal response, which means that the response comes after the beginning, which means that it's never linear phase. Very, very few things in the physical world are linear phase. One of them is the bottom end of an analog tape recorder, but that's sort of different. But very few things are, and so the right thing to do is to build converters with post response only, and that's been known for more than a decade. And in fact, now sometimes DAC chips build that in, but they still have a significant post response, and the A to D converters very typically don't have that. So yes, you could design converters which are more temporally accurate, and then we get closer, and then of course we can use the origami in a slightly different way to close that up. That's fine. The problem is we have to deal with the whole music archive, recorded music going right back, and so we have to be able to deal with every type of converter. Yeah.
But you essentially are doing that. You're replacing path filters with good ones.
Yes, exactly. Yeah, exactly. And by the way, that's at the front end, and at the back end, every MQA decoder is different because it is programmed to match the DAC chip that's in the converter. So its filters, its analog filters, its arithmetic is dealt with separately.
And if we come to the point where, because the band at which we're passing data increases all the way, so if at some point we come to a stream 96K, for example,
yeah.
Does that mean that we wouldn't have this problem necessarily because the ringing will be so far in the high frequencies, or will that be still a problem?
Remember the graph I showed you? It said you would think that was true, but in fact, brainstem responds to the envelope. Now, when ringing's happening up at 192, you'd think, well, the brainstem's not even going to respond to that. All we can say is that it makes a difference, and there is a benefit to deblurring. But it's a very tangled thing. You can't. It's the thing about listening test. It's hard to do to change one variable, and you can't think about filtering without thinking about quantization and dither, and those things all interact.
Thank you. I really appreciate it.
Okay.
No, L2 Records records everything at 352, and you would think that they'd be the last people that would want deblurring because it's got such good temporal response already, and they're the first people to want to do it.
Yeah, because they are a bit intense in their approach, and then it brings me to another question. Can I? I'm sorry.
Yes.
But it sounds better. Yeah.
Okay.
I want to just add one quick thing on this. The converters that we make now have an analog. The A to D converter has an analog front end running at 6 bits and 24 megahertz. So the amount of information that we capture at the very front is about what would be like 6,000 times more than 24,384. So we can capture a lot of information, and it gets reduced to 24,352. It's 6,000 fold, okay, during the summation, just to give you a perspective of how much you can capture and how much you retain.
And even chip converters are getting better and better. There is a commercial, is it a Sears that does 768 out of the box?
AKM.
But you still have to filter it. Can you stand up? Do you mind?
The very last one. I'm sorry, I'm taking all the times. Another question. You mentioned before that we say that the brain can perceive something like 5 microseconds.
Some tests go down to 1.
Yeah.
Andy Moore claims that some tests go down to 1.
So I just made a quick calculation on my cell phone, but basically it gives you like if you divide 1 by 10 at the -6, it gives you basically 200 kilohertz basically as a sampling rate. You would need to get that.
Well, not only that, distance-wise, it's very small. The sound traveling in air, it's very small.
So be clear, we're not saying that you need 200 kilohertz of audio. You've got to separate the two things. So yes, in order to have a 5 microsecond resolution, you need at least 100 kilohertz, maybe wider, of analog bandwidth, right? But it doesn't mean there are signals up there. What it means is that the sounds that arrive at our ears can be resolved to those sort of time differences. And the 5 microsecond difference can happen just inside the pinna reflections, or reflections coming from the room. So, like I said, you hear a sound many times. And so when we hear a musical instrument, the sound isn't coming from a point source, it's coming from many sources. So the way it's combined, these wavefronts arrive. And a lot of the work that's done, good psychoacoustic work showing, down to 10 microseconds, temporal microstructure is in the mid-range. And it's actually shown
frequency-wise. I was saying, in order to capture, if you want to capture an intense impulse, just an impulse.
I've got 3 slides. I'll show you about that.
Okay.
But first, I wanted to show you this one, which is what Miha's talking about. That in typical converters, which are delta sigma converters, which is like 99.9999% of what's around, the real point of analog to digital conversion is in what's called the modulator, which is running at 6 megahertz, 4, 5, 6 bits.
Actually, now at 24 and 6 bit.
24 megahertz, yes, but 6 bits. So,
really
but the key thing about the 6 bits is when you actually in silicon, you make a converter, it's very hard to have a large number of bits. And you have to have at least 3 to be PCM. 1 for the signal and 2 for the dither. So 6 is a good number. And what happens in the converters is that it goes down through a dividing chain. And every time we divide it, we end up, at a high rate, we end up with an impulse response. So at 384, it's narrow, and if we divide it down to 192, it's broader. If we come down to 96, it's a bit broader. If we come down to 48, now we're talking about plus or minus 4 milliseconds instead of plus or minus 50 microseconds. But it's still long. But actually, this is an artifact of the divider chain, as is not bothering to dither it properly, which is another whole question. And when we come to reconstruct it, if we've got 48K signal, it gets upsampled all the way back up to the modulator. And in the perfect world, there is a dotted red line there. What we'd like to do is join that to that and go away with all of this. The data rate would be huge, but conceptually, that's what we're trying to do. We're trying to de-blur the front end, get back to a representation of this analog, and at playback, get to that representation of analog.
And by the way, that's what DSD was. That's the basis of SACD, is a minimum amount of data at a very high rate. It wasn't a high enough rate, it turns out.
And it was 1 bit, but it started with taking the output of a 1-bit modulator.
Yeah.
That's exactly where it started. Now, I was going to show you about blurring, so talk among yourselves while I find the next slide.
The other thing in a real space is small differences. In a real acoustic space, there's chaos. It's hard to predict what small changes in source localizations result in. Think of a performer that's moving, and the incredible complexity of what's coming off an instrument, not only the back, the front, but everywhere in a 360-degree space. As that hits surfaces and is diffused, that complexity that comes back. Eventually, the ear gets a sense of meaning out of that, even though they're very small differences. And I think the temporal world has been ignored. We all think it's been ignored for too long.
So go right back to my first thing about what is high resolution. It's separating sounds. It's being natural. And this first graph shows. Ignore the orange curve for a minute, because that's the impulse response of an MQA chain from analog in to analog out. But all the other ones are the impulse response of air. 2.5 meters, 5 meters in red, right? 7.5 meters in blue. This is the way air blurs the sound. And so this is what we try to do. Now, if you look at what happens in current digital CD channel, has this kind of blur, and the reason you can't so high is it actually goes on over here somewhere. It goes on to 4 milliseconds, not 300 microseconds. There's the 192, and here's air, and here's what MQA does. So when you start to think about it in this simple analog sense, sometimes the most important ideas are very simple. That's what we need to do. And to your point, what happens if we hit an impulse? Well, here's what happens in air if we get 2 ticks, 25 microseconds apart. And these are shown, the first one smaller than the second one, because it can easily get lost. And, through 5 meters of air, you get a good representation. And this is amplitude. This is what MQA will do with it. But when we're at the back of the concert hall, that's what we hear. So air is going to smear the sound. Now, let's look at 48 kilohertz channel. A 48 kilohertz channel is basically equivalent to CD. It's the first one went missing completely. Smeared the two together. At 192 kilohertz, the conventional PCM chain can only just separate them. It's not clear from this picture whether the ear can separate those two events. All right? But air can. And here is MQA compared to 5 meters of air. So this is the kind of scale that we're talking about. That fine details can be separated. But I've drawn it as two impulses to make it easy for you to understand. But it could actually be, your girlfriend whispering in your ear, and there's sounds arriving many, many times, and this separation is what we're pretty wired for that. Okay, so.
Great.
What would it take to play more music?
More music, easy. I was going to try title one more time, if that's okay. Is that good?
Anything that is a little bit more density in the high end? I've never really heard a great number of title tracks, because it really is just come out, so I can't point to one. I apologize.
Well, I was going to play the fiddle.
Yeah.
But you can tell me, you turn it off when you're bored, okay? So this is a fiddler with a choir, 352.
And Bob Ludwig's hand is on the knob.
Bob Ludwig. So it's going to sound great because you're going to get the level just
right. Nice fade, man.
I do it for a living.
you should done by the best. All right? So let's go back to PowerPoint for a minute. So that picture I showed you of what goes on inside the A to D and the D to A gives you a much clearer understanding of why it's interesting to think about a lossless connection. But what we're really talking about is you can have a lossless pipe, but the A to D is lossy and the D to A is lossy. And that's the point. Mm-hmm. Converters are, right?
I have a question.
Can you do me a favor? Could you stand up? Could you take the mic?
So I just want to understand, like, the algorithm or whatever MQA does to process the signal would basically take care of generic pre-ringing because different converters would basically give you different pre-ringing, different post-ringing too, right? So, like, I just want to understand how the process happens.
So when we have time and we're doing what we call a white glove approach, we will characterize the A to D converter. If you have the A to D converter that was made with, we take a fingerprint of it and we feed that into the process, right? And we've got several A to D converters fingerprinted. And some very interesting examples of where that is quite radical. When you actually fingerprint, even if you get the actual one, it's very helpful. However, our encoder has got quite a lot of artificial intelligence built in it if we don't know the converter, or if it's come from a complex mix and there's like 6 or 7 different converters, that you just work out what you can do and make the best job of it. So it can be done generically, and it can be done specifically.
Perfect. Thanks. That's a great answer.
Hi.
Question for him.
Back in the bad old days when we were testing MP3s, we had people like Karl-Heinz saying, well, listen to the CD quality and listen to the MP3 and go listen to Tom's Diner, and at this point, listen for this particular thing. And that way we could take people who were completely blind to the artifact and in a short listening session, make them say, oh yeah, and they'd start hearing the same artifacts in all sorts of different things as well. And one of the things that I'm kind of looking for is, if I'm going to try and wow someone with the difference between the high resolution sample rate recordings and what they could end up with 44.1 or 48, are there particular pieces of music that you can say, hey, go get the high-res track of this and do the comparison, level match them, stick them in a good listening chair, and play this piece at high-res and then this same piece at 48, and tell them to listen for some particular effect within that.
You can, but it's very important that you get the right assets, because what you can't do is go out and get the high-res file and the CD and the MP3, because they're all mastered differently. So those all have to be made from the same core asset.
But the other thing is Karl-Heinz, as you were talking about Karl-Heinz Redding, has a particular view of the universe that's pretty well anchored in MP3. As recent as any panel he's done, he's not going to change. We're not trying to change his mind. I'm going to go so far as to say, although we're good friends with him, and he's a dear man, we're not going to change his mind.
Can I talk about my experience, because that's how I heard MQA for the first time. I was in Munich at the Hi-Fi show, and I went to see Bob's lecture about that was 2015 maybe, in the spring, and you played Keith Jarrett Cone concert, and what was remarkable about the before and after was the sound of the piano hammer, how it hits the string, and that was very obvious, kind of. We played it before, and it was hard and recorded too close. It was mic'd very close. It just sounded very, very hard. And then we heard the deblurred version, and that sounded like a real piano. And it was really, really very obvious to me that Bob was onto something when I heard it.
When in that recording, you hear the audience so much more clearly. But we really want to go back to find that real tape. So go back.
Mm-hmm. Right, yeah.
Okay, so Shostakovich,
I think it's time for Shostakovich.
do you want to introduce this?
Sure. Go about 11 minutes into the movement or so.
Okay, I'll start it and jump in. So
This is
can you keep the volume down on that?
We sent this over, the original 96K file, and Bob processed it with MQA this afternoon. We listened to it. It's recorded in Boston Symphony Hall last year. It's an original 9632, output to 24, and live performance of Boston Symphony. And it was an impressive demo of the MQA in the deblurring, and it's a modern recording. It was done just a year ago, so it is an example of what can be done to a current recording, and to make it a little more clear and a little better.
Is this where you want to be in it?
Sure, we'll play it out to the end about there. Yeah. Thanks.
Brilliant.
And the great thing is if that were on title, you could hear that exactly the same at home if you get a decoder. Thanks very much. Thanks for your patience. Thanks for your attention. Thanks for the great questions from Korea. And we'll see you all the next time. Cheers. And thanks to our panel. Thanks, guys, for coming to the panel. Thanks, Mihal, for fighting LaGuardia traffic. Thanks, Bob Ludwig, for driving all the way down. And
You're welcome.
And for the brilliant DJ job.
Did you drive?
How are you?
Just for my comprehension.
All right, all right. You moved. Come on over.
No, I'm fine.
We have been far. What do you know? Are we going to party? Because I stalked you and I realized you were original podcast that he ran hide behind the bush and watching.
What?
What?
Yeah, I don't
So you're
go
through
there.
that? But you're living, no, it was because Ryan told me you moved with,
I live with Jack.
Jack, yes. Okay.
Yeah, like I've been living with him since August.
So you guys like starting up a little engineering
No,
thing
not
going
even.
on? No?
Not even. Like,
Just roommates.
yeah, just roommates.
Who? Just chilling.
Well, I live with Jack.
Oh, that's where you live with us.
Yeah.
We're like, I'm not sure.